Hello everyone, welcome to this lecture. So, now for the next few lectures we will focus on abstract algebra and we will start with group theory. So, the plan for this lecture is as follows: we will discuss the definition of groups and we will see various properties of groups and we will also see various examples of groups. So, let us start with the definition of group. So, what is a group? Imagine you are given a set big G which may or may not be finite and you are given some binary operation. By binary operation I means it operates on two operands and this operation is over the set big G, that means the operands will be taken from your set big G. So, the set big G along with the operation O will be called a group if it satisfies certain properties which we often call as group axioms. So, let us see what are the properties that needs to be satisfied or the axioms which needs to be satisfied. The first axiom which we call as G1 is the closure property, and the closure property demands that you take any two operands a comma b from your set big G. If you perform the operation O on A and B, the result should be an element of the set big G itself, and that is why the name closure. Closure in the sense that it will not be the case that by performing the operation O on the operands A and B, you will obtain a member which is outside the set big G. It will be within the set big G itself, and this is true for every AB, namely when even for A equal to B as well. Okay. So, that is a closure property. The second property or the axiom is the associativity property denoted by G2, which says that, which demands that your operation O should be associative. That means it does not matter in what order you perform the operation, namely for every triplet of values A B C from your set big G, if you perform the operation AOB, you will obtain a member of the set big G, and then again if you apply the operation O on that member and C, the result will be the same if you do the operation in the following order. You do the operation on B and C first, that will give you an element of the set big G, and then again you perform the operation O on that element and the element A. The result will be the same. The third property or the axiom is the existence of identity denoted by G3, which demands that there should be a special element, in fact a unique element, which we denote by E, present in my set big G, which is called as the identity element, such that the identity element satisfies the following property for every group element. If you perform the operation O on the element A and the identity element, you will obtain the same element A, and this it holds even if you perform the operation on A and E or if you perform the operation on E and A. Okay, it does not matter in what order you perform the operation, the result will be A, and this should hold for every A. Okay. So, that is the existence of identity. The fourth property and the last property which you require from a group is that of existence of an inverse element, which demands that you take any element from the set big G, corresponding to that there should exist a unique element which I denote by a power minus 1, and that element a power minus 1 also should be present in my G itself, the set big G, such that the result of the group operation on A and A inverse is your identity element. I stress here that this a power minus 1 is just a notation. Okay. It does not mean that I am talking about 1 over A, no, that is not the case. This is just a representation, just a notation for a special element which I demand to be present in my group, such that this property holds. So, if your group, if your set G along with the binary operation O satisfies all these 4 axioms properties, then I will say that this set G along with the operation O is a group. Even if one of these 4 properties is violated, the set G along with the operation O will not be constitute a group. Okay. So, few important notes here. The operation O need not be commutative, because the group axioms only demand the operation O to be associative. It does not demand the operation O to be commutative. That means, the result of performing the group operation on A and B need not be the same as the result of performing the group operation on B and A. And as I said earlier, the element A power minus 1 should not be interpreted as numerical 1 over A. That is just a representation or notation for an element present in my set big G, which has the special property. So, now let us see some examples of groups. So, the set of integers Z, which is an infinite set, along with the operation plus constitutes a group. So, let us see whether all the 4 properties are satisfied or not. So, the closure property is of course satisfied. You take any 2 integers A and B and add them, you will again obtain an integer. The operation addition is associative over the integers. So, you take any 3 integers, it does not matter in what order you add them, the result will be the same. The integer 0 is the identity element. So, 0 is your identity element E. Why it is identity element? Because you add 0 to any integer A, you will obtain the same integer A. And the integer minus A will be considered as the inverse of your integer A, right. So, this minus A is actually A power minus 1 as per the notation. And you can see that you take any integer A, its inverse is minus A, because if you add minus A to A, then the result will be 0, which is your identity element. Okay. Now, let us change the set. So, here the set G was my set of integers. Now, I am changing my set G to the set of only non-negative integers, that I am not, that means I am not including 0 and I am not including negative integers. I am talking only about positive integers, and my operation is still the same, namely plus. Now, it is easy to see that this G along with my plus operation. So, the plus operation is the operation O, does not constitute a group. And which property is violated? Well, the closure property is still satisfied, associative property is still satisfied. Okay, by the way, when I am saying non-negative integers, I am including 0. I said earlier 0 is not included, but 0 is included. So, the identity element is still there, but the problem is that my 4th group axiom is not satisfied, because the inverse of an integer A will be minus A, but minus A is not an element of Z plus, because minus A is a negative integer, negative value, and negative values are not allowed in the set Z plus, whereas the group axiom says that the inverse element also needs to be a member of the set G itself. So, that is why the set of non-negative integers along with the addition operation does not constitute a group. Okay. So, we have seen now a group with respect to the plus operation. Now, let us see a group with respect to the multiplication operation. So, now my set G is the set of all real numbers excluding 0, and my operation O is the multiplication operation, and now you can see that all the 4 properties of group are satisfied. Multiplying any 2 real numbers will give you a real number. Multiplication is associative over the real numbers. The real number 1 is the identity element, because you multiply 1 with any non-zero real number A, you will obtain the same non-zero real number A, and you take any non-zero real number A, its multiplicative inverse will be 1 over A, and 1 over A is well defined because my A is non-zero. So, 1 over A indeed exists and it belongs to the set of non-zero real numbers. So, all my 4 group axioms are satisfied, and hence this set constitute a group. Whereas, if I take the set of non-zero integers, then it does not constitute a group with respect to the multiplication operation. Now, let us see which property gets violated. So, the closure property is still there, associativity property is still satisfied, the identity element 1 is indeed present in the set of non-zero integers. The problem is that the existence of inverse is not guaranteed, because the inverse of an integer a will be 1 over a, but 1 over a may be a real number. Okay. It may not be an integer. So, that is why the fourth property is violated, due to which this does not constitute a group. Now, let us see some other interesting examples of groups. So, imagine n is a modulus, a positive integer, and I define the set Z subscript n to be the set of integers 0 to n minus 1. So, basically it is the set of all possible remainders which you can obtain by dividing any integer. It could be positive, it could be negative, whatever possible remainders that I can obtain by dividing an integer by n, the set of those remainders is my set Z n. Now, I define a new form of addition over this set. I call it addition modulo n, which is denoted by this notation. So, addition modulo n of a and b is defined as follows: I add a and b and then take a modulo n. The result will be called as the result of addition of a and b modulo n. So, now my claim is that this set Z n, which is a finite set because n is an integer, positive integer given to you, and I know that this set Z n has indeed n values. So, my claim is that this set constitutes a group with respect to this operation of addition modulo n. So, let us see whether the four properties are satisfied or not. So, the closure property is indeed satisfied. You take any integer a and b in the range 0 to n minus 1, you add them, and then if you take modulo n, the result will be r, and r of course will be in the range 0 to n minus 1. So, hence it is a member of Z n. So, closure property is satisfied. It is easy to see that the operation of addition modulo n is indeed associative, because it does not matter in what order you perform the addition modulo n over 3 values a, b, c, the result will be the same as a plus b plus c modulo n. The element 0, which is indeed present in my set Z n, will be the identity element, because if I add 0 to any element a from the set Z n, and then if I take modulo n, the result will be a itself, because since a is a member of Z n, that means a is somewhere in the range 0 to n minus 1. Now, if I add 0 to a, the value of a does not get incremented, it remains the same. And now, if I take modulo n, the effect of mod will not actually take place, because my value a at the first place itself is less than n. So, the result will be a. Now, what about the inverse? So, my claim is that the number minus a, which is defined to be n minus a in the context of this operation addition modulo n, constitutes the inverse for any element a, right. So, remember when I took my group to be the set of integers and my operation was the regular addition, then a inverse was defined to be minus a, and minus a indeed belongs to the set of integers. So, the minus a in the context of set of integers modulo n will be defined to be n minus a, and it is easy to see that n minus a is again an element of Z n, because if a belongs to Z n, that means a is in the range 0 to n minus 1, then that automatically implies that n minus a is also within the range 0 to n minus 1. Okay. So, that means I am not, my inverse here is not a member which lies outside the set Z n, it is a member of Z n, and the property of this minus a is that if you add it with any a and then if you take modulo n, the result will be n modulo n, which is 0, and 0 is your identity element here. So, this is now an interesting example of a variation of addition operation with respect to a set, and together they constitute a group. Now, let us see a corresponding variation of the multiplication operation, which we call as multiplication modulo n. So, let me first define a set Z n star, and Z n star is basically the collection of all integers A in the set Z n which are co-prime to your modulus n. Okay. So, for instance, if n is equal to 10, then my set Z 10 star will be the following. The value 0 will not be there because 0 is not co-prime to 10. The value 1 will be there because it is co-prime to 10, 2 will not be there, 3 will be there, 4 will not be there, 5 will not be there, 6 will not be there, 7 will be there, 8 will not be there, 9 will be there. So, this will be the value of Z 10 star. Okay. And now I define a new operation, a variation of multiplication over the elements of Z n star, which I denote or call as multiplication modulo n, denoted by this notation. So, the result of A multiplication modulo n with P will be the following. I multiply A with P and then take a modulo n, that will be the overall answer. And my claim is that this set Z n star with respect to this operation of multiplication modulo n constitutes a group. So, let us see whether the closure property is satisfied or not. So, for closure property I have to prove that you take any pair of integers A b from the set Z n star, their product modulo n should be also a member of Z n star. So, since A and B are members of Z n star, they are individually co-prime to n. Now, let R be the result of A b modulo n, that means I multiply A with B and then take mod n, I get the remainder R. Of course, R will be in the range 0 to n minus 1, but that does not shows the closure property, because I have to show that R belongs to Z n star, namely I have to show that R is also co-prime to my modulus n. And indeed my claim is that R is co-prime to the modulus n, because since A is individually co-prime to n, P is individually co-prime to n, I get the conclusion that A b is also co-prime to n, because if A b is not co-prime to n, that means if there is some common prime factor P which divides A b and n, then I get a contradiction that either A is not a co-prime, A is not co-prime to n, namely the same prime is a common factor of A and n, or B is not co-prime to n, which is a contradiction. So, GCD of AB is co-prime to n, and from my rules of division I know that R is this AB minus some multiple of n, because R is the remainder which you obtain by dividing AB by n. That means, as from the rules of division, AB is equal to some k times your modulus. So, k is your quotient plus the remainder R. So, the value of R is this. So, now since AB is co-prime to n and R is this value, I get the conclusion that indeed R is co-prime to n. Okay. Right. So, that shows the closure property. Now, let us see whether the operation multiplication modulo n is associative or not, and it is associative, because if you take a triplet of integers A B C from Z n star, it does not matter in what order you perform multiplication modulo n, the result will be the same that you will obtain by multiplying A B C and then taking modulo n. The element 1 is always present in Z n star, and it is the identity element, because you take any element A belonging to Z n star, you multiply 1 with A, and then if you take modulo n, the result will be A itself, because since A is a member of Z n star, A is strictly less than n. So, effect of mod n will not take place. And now I can claim that for every integer A belonging to Z n star, since the GCD of A and n is 1, then recall that from our earlier lecture, in the earlier lecture, one of the earlier lectures, we proved that if A is co-prime to n, then multiplicative inverse of A modulo n exists. That means, there always exists an integer B, which will be a member of Z n star, such that if you multiply A with B, and then if you take mod n, the result will be 1. Okay. And that B you can always find out using extended Euclid's algorithm. So, that shows that this set Z n star along with this variation of multiplication, namely multiplication modulo n, constitutes a group. So, now we have seen examples of several groups, namely we have seen examples of 4 groups. Each group has a different structure, namely their elements were different and the operations were also different. Okay. And these are not the only examples of groups, there are, I can give you infinitely many examples. Okay. Now, the point is that even though they are different sets with different operations, they have a common property. And what is the common property? All of them satisfies the 4 group axioms. It does not matter whether you are talking about this group comma O, or whether you are talking about this group comma O, or whether you are talking about this group comma O, or whether you are talking about this group comma O, and so on. All of them will have the 4 axioms being satisfied, namely the closure property, the operation is associative, an identity element will be there, and inverse element for every group element. So, what we can now do is, and that is what precisely we do in abstract algebra, instead of studying each of these sets individually and separately, right, and deriving properties of each of these sets separately, we will abstract out all these sets by a common template, by a common structure, okay, and all the operations that were there in the individual sets that were there available with respect to individual sets, they are also abstracted by a single operation O, and then we will study the abstract set and along with the corresponding abstract operation, assuming that they satisfy these 4 properties, and we will derive whatever interesting properties that we can derive from for the abstract set and the abstract operation. And now I can say that whatever properties that I have derived for the abstract G and the abstract O, they hold for any instantiation of the abstract G and abstract O. So, what I mean by that is, assuming that the properties G1, G2, G3, G4 are satisfied for this abstract G and O, and say based on these properties I derive several interesting properties, say P1, P2, P3, P4, P5 and so on, Pn, then I can say that all these properties P1, P2, P3, P4, Pn holds for this instantiation of the group, 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 or any instantiation of the group that you can think of. And this is very interesting because I am not deriving these properties separately and individually for each set, namely set of integers, set of non-zero real numbers, set of all integers which are co-prime to my modulus n and so on. I am deriving these properties once for all for this abstract group G with the abstract operation O. So, that is why abstract algebra is a very interesting topic in computer science, because once we do this abstraction and derive algorithms properties for this abstract group and abstract operation, then depending upon our requirement, our application, we can instantiate the group and the operation with some concrete set and concrete operation, and then apply these properties that we have derived on those corresponding concrete instantiations. And this is very helpful in several areas of computer science, especially in cryptography, which we will see later. Okay. So, that is why when we say abstract algebra, it might look very abstract to you, because we are talking about an abstract set and abstract operation and keep on deriving properties, but when we instantiate those sets and operations by a concrete group, and concrete operation and then fit it in an application, then you will see the real application of the theory that we are developing in the abstract algebra. Okay. So, now what we will do is from now onwards we will not be focusing on concrete groups and the corresponding operation, but rather we will be focusing on an abstract group and corresponding operation, right. So, I will say that okay, my G is a group, I do not care what exactly are the elements of my group G, I will just give them some names. I will not know whether they are integers, whether they are real numbers, whether they are vectors, whether they are matrices, I will not go into the exact instantiation. And in the same way I will denote my corresponding group operation by O. I will not go into the details whether my operation O is the numerical addition, numerical multiplication, or whether it is addition modulo n, or whether it is multiplication modulo n, or whether it is matrix multiplication, or whether it is dot product of vector or scalar product of vector and so on. Okay. And then I will just assume that my group axioms G1, G2, G3, G4 are satisfied and derive whatever interesting properties I can derive for the groups. Okay. So, it turns out that there are two popular notations which are used for the abstract group operation O. Okay. The first notation is the additive notation. I stress that this is just a notation, instead of writing O I will use the plus symbol, right. And if I am using the additive notation, then the corresponding E I will denote by this 0. So, I stress here that this plus is not the numerical plus, it is just a notation that I am following the additive notation, and 0 does not stand for the numerical 0, it is just a representation for the identity element of my group. If you do not want to bring the plus and O, that is fine, you can just stick to your operation O itself and you can use E as your identity element. But sometimes since we are very much habituated to plus and 0, right, that is why sometimes we find it convenient to use instead the notation plus and 0 for the identity element. And if we stick to this additive notation, then the additive inverse, namely for the element A you will have a corresponding A power minus 1 such that A operation A inverse is your identity element. So, what I am saying here is that if I am following the additive notation, then sometime for convenience I may use minus A for representing the additive inverse, namely minus A is the representation for that group element which when operated with A will give you the identity element E. So, examples of groups which come under the umbrella of additive notations are these groups. So, you can recall that the set of integers with the operation plus was actually an additive group. The set of integers modulo n along with the operation addition modulo n forms under the umbrella of additive group and so on. Whereas, another popular notation which is used for abstract group operation is the multiplicative notation, where the operation O is instead represented by the dot, but this dot does not mean multiplication, numerical multiplication. This is just a representation for convenience, and if I am following the multiplicative notation, then the identity element E will be represented by 1 and the multiplicative inverse will be represented by A power minus 1. Again A power minus 1 does not mean 1 over A, it is just a representation if I am following the multiplicative notation. Okay. So, now let us derive some nice properties that are true for any abstract group. So, the first property that I am going to derive are the left cancellation rule and the right cancellation rules. So, the left cancellation rule says the following: if you take any arbitrary group elements x, y, z, a, b from the group, and if it is the case that x operation O is same as x operation z, then I can conclude that y is equal to z, and this is called as the left cancellation rule. Why cancellation? Because from the implication I can say that this has the same effect as if I am cancelling out x, and in the same way you have a corresponding right cancellation rule, namely the rule says that if A operation x is same as B operation x, then you can cancel out x and conclude that A is equal to B. So, let us prove the left cancellation rule. The similar proof you can give for the right cancellation rule, and I will give the proof for any abstract group G along with the corresponding abstract operation O, and I will give a direct proof. So, imagine that your premise for the left cancellation rule is true, namely x operation y is equal to x operation z. Now, since x is an arbitrary element of your group, and for convenience I am following now the multiplicative notation. So, the inverse of x is also present in your group. So, what I can say is that the result of x inverse operation x operation y will be the same as x inverse operation x operation c, right. And now, since my operation O is associative, I can rearrange the terms here on the left hand side as well as on the right hand side, but the property of inverse is that if you perform the operation O on any element x and its inverse, you will get the identity element, and the property of the identity element is if you perform the operation on the identity element and any element y, you will obtain the same element y. So, I come to the conclusion that y is equal to z, which is indeed the conclusion. Similar proof you can give for the right cancellation rule. Now, an interesting corollary of the left cancellation rule and the right cancellation rule is the following. Imagine you take a group which has say n number of elements g 1 to g n, and you take any group element g I. Now, if you perform the group operation on g I and various elements of the group, say you perform the operation on g I and g 1, g I and g 2, g I and g n, of course, from the closure property all of them will be elements of the group itself, right, because g I is an element of group, g 1 is an element of group. So, the result that I will obtain by performing the group operation will be a member of group. Same is the case for g I operation g n, but the question is whether my results that I will obtain will be same or different. So, I will obtain n elements. So, call the first value that I obtain as a 1, call the second value that I obtain as a 2, and call the second last result that I obtain as a n. The claim here is that the result that I will obtain, namely a 1 to a n, they are all distinct, the result will not be repeated, and this is because suppose the result of g I operation g s is same as the result of g I operation g t, then from my left cancellation rule I come to the conclusion that g s is same as g t. So, contrapositively, if g s and g t are different, then the result of g I operation g s is different from g I operation g t, which shows that each of these results are distinct. Now, let us define another special group which we call as abelian group, and then we will define group order. So, a group is called as an abelian group if it is a group and it satisfies an extra axiom, namely a fifth axiom, which says that the operation O is commutative. So, it is not the case that every group is abelian, because the operation O may or may not be commutative, but if the operation O is commutative, then my resultant group is called as an abelian group. So, for instance, the set of integers with respect to the plus operation is abelian, and there are other examples of abelian group as well. Now, let us next define group order. So, the group order is basically the number of elements in the group G. Now, depending upon whether the number of elements is finite or infinite, namely whether the cardinality is finite or infinite, I will either get a finite order group or an infinite order group. Okay. So, with that I conclude today's lecture. Just to summarize, in this lecture we started our discussion on abstract algebra. We discussed about the definition of groups, abelian groups, we saw various examples, and we also saw left cancellation rule and the right cancellation rule. Thank you.